Hello, everyone. Thanks for coming to this feed-forward talk on lessons learned on Apache Flink applications availability in Kinesis Data Analytics Service. My name is Praveen Gattu. I head the engineering team for Kinesis Data Analytics Service. Presenting this talk along with me is Hwanju Kim, Senior Software Engineer in Kinesis organization. The agenda for this talk is we're going to go briefly over various streaming options and the solutions that AWS and Amazon present for customers. Then we're going to go a little bit into depth on Amazon Kinesis Data Analytics Service for Apache Flink, which is the focus of this talk. Some of the problems we ran into as we were measuring availability of Flink applications. What did we do about it? What improvements did we do? What were some of the lessons we have learned in the process? And then we'll be closing the talk with some of the future enhancements we are working in this area. So to give a very high-level overview, Amazon or AWS offers 4 different services which helps customers manage their streaming data. 2 of these services are Amazon Kinesis Data Streams and Amazon Managed Streaming for Apache Kafka. These 2 services are meant for customers to ingest or capture their streaming data, store them, and then ability for their consumers to read off of this data. Kinesis Data Streams is a homegrown solution of in AWS, and Amazon Managed Streaming for Apache Kafka is a managed service for open source Apache Kafka. While these services allow customers to capture the data, we do have services which allow customers or make it easy for customers to process the streaming data. And the 2 services we have in this space is Kinesis Data Analytics and Amazon Kinesis Data Firehose. So Amazon Kinesis Data Analytics service allows customers to build stream processing applications and then run them in a serverless fashion. Amazon Kinesis Data Firehose is a very easy to use service whose main purpose is to provide customers with a very easy configurable option to have their streaming data delivered to some of the analytics destinations such as S3 and which is data lake or data warehouse products. So the focus of this talk is going to be Amazon Kinesis Data Analytics Service. This service was launched in 2016. There are effectively 2 flavors of the service. The very first iteration we launched allows customers to use SQL as a way to express their stream processing logic. In 2018, we launched a second iteration of this product where now customers can build their applications using Apache Flink framework, provide us the jar, and then we effectively run that for customers in a serverless fashion. So focus of this talk is going to be on the Apache Flink side of the service. So how do customers interact with Kinesis Data Analytics Service? First and foremost, customers use the IDE of their choice to build a Flink application. Once they have the application, they can build a jar, and then on the service, they can create an application, specify the jar as part of that application, and then with a very simple API, they can start the application. With these 3 quick, easy steps, now they have a fully functioning application. The service also provides customers with a very easy to use APIs around managing the lifecycle of applications, such as ability to update the application, stop the application, and then allows for customers to do state management. So the benefit here is customers now have a fully functional service or fully functional application, with a very simple APIs, and the application runs in a serverless fashion. This slide tells how we run the Kinesis Data Analytics Service, again at a very high level. We have web server, which accepts customer requests such as ability to create an application or start an application. We have control plane that we stood up, which is responsible for ensuring the actions that the present customers have given are acted upon, such as making sure the application gets started, ensuring the application, when the customer issues an update, the update action is acted upon. Along with it, there are other components that exist in the control plane, which is responsible for ensuring the health of the application is maintained. If there is any scaling activity that needs to happen, that takes place. On the extreme right is the data plane. We run Apache Flink applications in the Kubernetes using Amazon's managed Kubernetes service called EKS. Now, we're not going to go into too much depth about the data plane and how it is built. This could be a talk on its own, but the idea here is to set the context, which could be helpful as we delve into the talk. So what does service do behind the scenes when customer makes an application to start? We do a few things. The first and foremost is we set up the compute infrastructure so that the application can be installed. Then we set up the Zookeeper ensemble so that the application is running in a highly available mode. The third is we set up security isolation. And this is probably the key element in our service. Since we run multiple customer applications and run them in a multi-tenant EKS cluster, and security is paramount in any of Amazon services or AWS services. So we make sure that the security isolation is maintained in terms of network boundaries, in terms of routing tables, so that there is no cross communication between applications. At the same time, we allow customers to use their resources in the VPC, so we set up the VPC connectivity. We also make sure that the application comes up with a RocksDB state backend, and then Amazon S3 is also used for a durable state storage. Again, these things we do because we want to make sure applications are by default set up such that there is no data loss in terms of processing the data. At the same time, we also bring up other components such as Prometheus scrapers to ensure, and the Fluentd scrapers to ensure the metrics and logs are delivered to Amazon CloudWatch so that the applications are easy to debug if an issue happens. At the same time, on the control side, we do set up other monitoring components in order to ensure scaling and monitoring or the recovery of applications happen. With that being said, there are a few things we have done as we were building the service. We looked at the various options Apache Flink comes with, and we were looking at the core tenets we want to make sure the service operates with. And there are two core tenets we always make sure Amazon services adhere to. One of them is the services should be highly available, and the services should be having a durable data storage. In this case, when we were looking at those tenets, there were a few defaults we had to override. For example, checkpointing. We turned them on by default for all customer applications, and we use RocksDB state backend by default. Now, customers do have options to turn them off if they want to, but these things turn on by default, and we do that so that we don't lose any data when there is a interruption or maintenance activity that has to happen. At the same time, we run Job Manager in highly available mode. Again, availability is very paramount for AWS services. On an update or a stop, we always by default, attempt to take a save point. Now, again, customers can choose to turn them off, but by default, we take a save point. And on a restart, we try to use the latest save point that is there or a customer chosen save point to restart the application. Now, these things, again, the core tenets we are trying to follow here is to make sure the applications are highly available, and then the durability is maintained. So with this context, let's look at what are some of the problems we were running into. So for any managed service, a most important thing is availability. Now, in order for you to maintain availability, you need to measure availability. So we were looking at various metrics Flink offers in this space so that availability can be ensured. And these are some of the metrics Flink offers. There was one metric which we looked into, which is the downtime. Downtime is the amount of time the amount of time it has elapsed where the application is not making progress or is down. So this metric was interesting to us, and we started tracking this metric as a way or as a proxy to ensure the applications are available. And when we started tracking this metric, this is how the graph looked like. Now, there are two things that are obvious in this graph. One is the graph is very spiky. The second is the graph never settles down to zero. Now, when you have this kind of a graph, it is really not that actionable. So we cannot set a metric we cannot set an alarm, because if we do, its alarm is always going off. At the same time, alarm is never recovering, right? So as an operator or as a service owner, this metric becomes not actionable for us. So why is this metric noisy? There are a couple of reasons. So an application can go down for broadly two scenarios. One is a system or an infrastructure issue, which could be like a hardware issue that could be happening, or there could be a bug in the Flink framework itself, which can cause an application to go down. The second could be customer could be submitting us an application code which can have issues, which can have bugs, or which can run into failure modes, which can cause the job to go down and then Flink to recover the job. In our experience, what we have noticed is, for the most part, these issues come from customer submitted code. Customers submit code where such that the sources and sinks may not be present, or the permissions may not be present on these sources and sinks. And when these kind of issues happen, application code retries for a certain period of time, and when the exception is thrown, the job restarts. Or there could be bugs in the code. We are all software engineers. There are bugs in the code, especially during development phase, there will be bugs in code. And these bugs can manifest themselves as resource exhaustion, such as out of memory, or there could be a file leak, which can translate itself as too many open files. Again, when these things happen, the job can restart. So what were we trying to do? What we are trying to do is to get to a point where we can measure availability such that this customer noise is removed from the measurement, and we can get a true measurement of applications availability, which is induced by system fault. And I would like to invite Hwanju to take us to the next part of this talk about how did we go about doing it. Hwanju?
Hi, I'm Hwanju, a software engineer at Kinesis. I'm taking over to present how we have measured Flink application availability in our service. Let me go over the challenges we try to address step by step. Firstly, I'm going to talk about how to measure uptime and downtime as a fundamental requirement for availability measurement. So, what is application downtime? One is application level downtime, which is the time during which an application is not making any progress of record processing. So such no progress can be due to catch-up time during replay from the checkpoint if the crash happens, or your user-defined function is stuck or throttled by external resources. This definition is high-level downtime from user's perspective, but is too application-specific to be measured by service provider, as various factors from application artifacts can affect this type of downtime. Second approach is service level downtime, which can effectively measure the time that application is not in running state. It is fairly straightforward from the viewpoint of the service, but conversely, it may be too low-level view from users. However, Flink provides various useful metrics for users to measure application level progress such as source latency and event time lag, so this downside can be compensated by those metrics. As a service provider, we focus on service level downtime. To measure service level downtime, we wanted to know whether an application is in running state or not. So we looked at job state machine managed by Flink runtime. This is pretty simplified state machine where many other states are omitted for presentation purpose. So you can see the full state machine in Flink document shown below. As you can see, it has running state, which is what we want. So simply regarding running time as uptime, while the rest of states as downtime seem to be straightforward, and this is also what Flink provides as uptime downtime metric. But it wasn't necessarily true, and we needed to zoom into the running state further. As shown here, Flink implements a job into a graph formed by multiple user-defined tasks. So once the job transitions to running state, it's just to simply ready to schedule individual tasks from a job graph. In the scheduling stage, Flink Scheduler tries to find the resource called the slot in Available Task Manager to execute the task. And once available resource is reserved, the task is deployed to the allocated task manager. And then finally, the task can run user-defined function on the task manager. So while scheduling and deploying, a task is effectively not up and running. So only once those steps are finished, we can see user code actually starts running. Since a job can consist of more than one task, we need to track individual task states to determine if an application is actually up and running with all of its tasks. To take that into account, we introduced job tracking state, which is finer-grained job state only for tracking purpose. A job tracking state effectively divides a single job state into multiple sub-states and is derived from underlying job and individual task states. It's extensible, but currently for our purpose, we divide running state into scheduling, deploying, and running sub-states. So in this refined state machine, once a first task is scheduled, it goes into scheduling. And once the first task is deployed, transitioning to deploying state. And finally, once after all the tasks transition to running, we consider that uptime starts ticking. Job tracking states allows us to measure time elapsed in each state, like left-hand side. And we can now consider running time as uptime, otherwise downtime. This turned out to be a much better standard to avoid the forced measurement, as we've observed non-trivial downtime takes place in scheduling phase by system issues. So now downtime is effectively failover time, and we started figuring out what caused such failover. The failure can happen either by user or system issues. Users as programmer has unlimited freedom to fail application. But as a service operator, we wanted to focus on failures caused by system not being distracted by the issues introduced by users' artifacts. As a first step, we can look at how Flink can perceive failure. Flink is written in Java and has pretty clear state machine in which when failure happens, an exception is thrown, switching any state to failing state, shown as red arrows in the figure. Moreover, to avoid stuck state, configurable timeout is defined for each state. So when timeout happens through exception, Flink would know that something went wrong, initiating failover. So we can take a look at how to classify such an exception into user versus system failure. So we introduced exception classifier, which is effectively rule-based label component based on how Flink runtime invokes user code. And we also analyzed exception data gathered from production for better classification. As shown here, each rule can be defined as an exception filter and each filter is pluggable and configurable in Flink code config file. The configuration change can be detected without restarting Job Manager to allow operators to reconfigure the filters on the fly during operation. This is mainly because as usual classification problem, there could be misclassification to amend on runtime. The classifier begins with system failure type so that we can be conservative by treating unfiltered and unknown exceptions as system issue. With the input of exception and context like exception graph, each filter may label failure type based on its logic. So let's look at some filters. One major filter is user function filter. Flink programmer define their logic such as source, map, filter, sync, and so on in user-defined function or UDF. As shown here, each UDF in a job graph is internally mapped to UDF encapsulated as an operator, which is run by each task on top of assigned task slot in Task Manager. So all of the components except UDF is considered as Flink runtime system, but as the UDF runs the user code, if an exception is thrown from UDF, we can consider it as a user issue. Another similar filter is user class loader filter. Flink has a separate class loader for user artifacts, including their code and its dependency. While system class loader is responsible for loading Flink runtime, including network and state management. So if an exception is thrown from a class loaded by user class loader, it comes from user submitted artifact. And since service provider treats user artifacts as a black box without any control, such exception is classified into user. It's only applicable to model where user submits a jar to Flink cluster, but not to a per job cluster where user artifacts may be embedded in system directory. So in that case, this filter can be excluded. One question is, what if an exception from user code is just a victim of system issue, such as network problem? The answer is once such issue happens, runtime components like network layer, scheduler, and heartbeat monitor generally detects the problem as well, so to be classified as system failure properly. Next filter is user serialization filter, which is dealing with one of the challenging problems. Flink allows programmers to register their own custom serializer to Flink. But any failure from such a serializer takes place in Flink runtime, not from UDF or user artifact. So this is sort of injected user failure to runtime. So we analyzed code path as well as data and added the rules that detect exceptions from type serializer and type serializer snapshot, which are interface for custom serializer and schema evolution. In addition to that, we added state migration exception to detect incompatible states and stream task exception for user config serialization error. Another one is the user API filter, which catches invalid use of Flink public API module, which is part of runtime. Based on the analysis, we conservatively chose this small set of exceptions as user issue. Finally, there are out of resource filters. Out of resource exception is typically blurring the boundary between user and system, since the exception itself is thrown from virtually anywhere, and that could be a victim, not necessarily a culprit. And tracking resource provenance, like by doing heap object graph analysis on runtime, is practically infeasible as it's too expensive. Our approach is to label such errors separately, other than user versus error system, and differs analysis and recovery decision to human operators. So we added out of memory and too many open file filters, which are most frequent resource errors. Now that we have downtime tracking and classification, let's put those things together. We consider the exception that triggers state transition to failing is the cause of failover. So all the downtime during that failover stages is attributed to the cause of the failure, which is decided by exception classifier. So on the right-hand side, now we can label the cause of each downtime, so we can gauge system downtime. Typically, one failure causes one failover, but interestingly, we have noticed that multiple cascaded failures are not uncommon in real world. And in other words, another failure can happen during failover, which can possibly have a different failure type. For example, in this figure, while running, user code throws an exception, triggering failover, whereas downtime is accounted to user. Some system issue can happen and make scheduling to be timed out, which it triggers another failover where its downtime should be accounted to system. Finally, system issue is either transient or recovered. Original failover could be finished, reaching running state again. As this last downtime is from original failover, regardless of nested system failure, this downtime is accounted back to user. So to address this type of nested failover loops, we implemented spec-based downtime tracking. Finally, let me move on to how we have been doing operations with this classified downtime. As expected, metric is the way for us to have visibility to do operation. From the classified downtime, we set the state and failure type to metrics variables, which is also called like labels or dimensions in different metric systems. And downtime is exposed as a gauge metric value. Then these metric values are exported through Flink metrics framework, where we use Prometheus metrics reporter, and then our service Prometheus server periodically scrapes this data and pushes it to AWS CloudWatch. There we do set alarm and do dashboard investigation. As shown here, we do some aggregation and transformation of raw metrics using Prometheus rules for better visibility. At CloudWatch, the top graph shows uptime and downtime increase for each state and failure type from an application with constant failures. These raw metrics are useful for deeper diagnosis, but it's not so useful for operation. So we transform the raw downtime metrics to Boolean state labeled with each failure type. The bottom graph is from a different example where an application was constantly failing with user exceptions. But during failover, it kept leaking heap memory, eventually running into out of memory. As you can see on the right-hand side, interestingly, out of memory started affecting system components. In this case, Flink scheduler couldn't allocate such unhealthy task manager. So in this view, we can easily identify historical failure transitions. Here are some lessons learned from engineering perspective. Like any other classification problem, failure classification is hard, especially because Flink is large and rapidly evolving. So classification needs to be more generic, not depending on specific exception types and messages. User function and user class loader filters help much, but still need non-trivial special filters. And as a general purpose stream processing platform, Flink gives programmers unlimited freedom to induce various failures. In this space, as a trade-off, declarative programming such as SQL, which is also supported by Flink, would reduce such failure surface by limiting such high degree of freedom. Next, as a general problem, Flink doesn't provide isolated sandbox for user execution environment by hosting user code with Flink runtime in the same JVM. To deal with this problem, Flink can allow user code to be hosted in a separate process or container, but performance will be impacted as a trade-off. Last one is Java exception may not contain full context of why failure happened, especially from externally triggered failures. For example, herpy timeout or scheduling timeout exceptions do not contain the reason why it happened, so we had to conservatively consider those as all system failures. Some can be caused by user issue like out of memory or incorrect slot sharing group assignment. For this issue, external health monitor can compensate the limitation by providing more context outside Flink. And this is the second set of lessons from operation experience. The downtime we have experienced is not just from infrastructure, but also from software issues. Major issues have been mostly from scheduling failure, which manifests itself as slot allocation timeout. And then they are due to code bug like a race condition and inconsistent state. The last two issues are what we reported and upstreamed the fix with the aid of this availability metrics. The second one is from failed timeout guards for stuck cancellation due to out of memory. So indeed, sometimes timeout safety net was not working properly, so failover was completely stuck. This issue is also what we reported and upstreamed the fix. Secondly, those software issues are mostly coming from failover stages, which means scheduling and canceling are normally fine as long as application is healthy without any failure. But once the application and its task manager become unhealthy, failover stages may be exposed to uncommon paths like race condition. Next is that such a failure is typically started with minor user issues like permission error, but throwing such an exception to Flink triggering full job failover is not really helping, but instead making things worse, causing cascaded failures. So Flink programmers should think through what exceptions to catch and handle inside the operator, not blindly throwing it to Flink, triggering unnecessary failover. Finally, resource overuse is typical, and this issue oftentimes impacts system components, making operation challenging. Based on the lessons, we've been working on auto recovery system. We've noticed that the majority of failures, especially software issues, are recoverable by task manager restart. And also, Job Manager already maintains and exposes rich information about task manager status. So our monitor system proves health from the Job Manager REST API, and once unhealthy component is detected, it automatically takes recovery action, which is typically restarting failed component after gathering relevant information for later investigation. This is effectively baking human operators' knowledge to software to minimize the downtime as well as operators' burden. In conclusion, availability is key metrics for long-running applications like stream processing. For platform providers like AWS, it's mainly for better operation, focusing on service-related availability issues, filtering out frequent failures caused by user code or configuration. And since long-running application can run for days and months, such metrics can help us do causal analysis about when an initial issue happened and how different failures have occurred as time goes by. Not just from the service provider, developers can also use these metrics for better debugging before deep log dive, which normally takes long time to spot relevant logs because huge volume of logs with a lot of noise. And as mentioned, the exception filter is pluggable. So developers can have custom filters and labels to enable customized downtime metrics for their own purpose. Here's the references for mailing list discussion and design. So you can find more details from these references. Thanks for attending this talk, and we are happy to take the questions.